Hi everyone, I'm Changhwa from 42 and I will be presenting our AACV work on long-tail recognition problem. This is a collaboration with Junho and Eunji. Let's start with motivation. It is difficult to learn high-quality representations in a long-tail environment because it overfits a limited number of tail class samples. For example, figure on the right shows tail class representations learned using cross-entropy loss. As you can see, we cannot expect satisfactory performance from the tangled representations. To quantify the quality of learned representations, we freeze the feature encoder and train a linear classifier using the test dataset. Then the accuracy of the linear classifier can be thought of as the upper bound accuracy, and we define it as feature accuracy. The learned representation's feature accuracy is 58.3%. In other words, any classifier cannot get an accuracy better than 58.3% with the learned representations, regardless of how we fine-tune it. Accordingly, it is crucial to learn high-quality representations under a long-tail environment to achieve higher performance. Let's move on to the overall framework. In the training phase, we employ mutual learning loss to learn high-quality representations. Mutual learning loss distills knowledge between core models. Core models' interclass correlation information helps each other avoid falling into local minima. In the long-tail recognition, a model is especially prone to falling into short minima since the cardinalities of tail classes are limited. We exploit the mutual learning loss to find more robust minima under the long-tail circumstance and acquire better representations. In the inference phase, PC softmax is used to balance the bias predictions. We compare the proposed method with recent approaches for several long-tail recognition benchmarks. Table on the left shows that the proposed method outperforms state-of-the-art methods by a large margin on ImageNet-LT. Furthermore, as shown on the right, our method even improves the performance of the Mensa subset and surpasses all other methods on all category subsets. To investigate the effectiveness of mutual learning, we train a model independently as well as a model with the mutual learning loss for comparison. We can observe that the representations learned with mutual learning achieve higher accuracy than those learned independently on all kinds of classifiers. Improving the quality of representations through mutual learning is easily adaptable to other methods. To demonstrate, we apply the 2x mutual learning model to baseline methods. As shown in table, all of the method's accuracies have improved by a significant margin. Left figure shows that few-shot classes exhibit higher prediction differences than the main-shot classes throughout the training process of independent learning. This suggests that the training result for tail class samples is highly stochastic and that it is easy to converge to a less generalizable solution. In figure in the middle and right, we can observe that independent learning converges to a lower training loss but a higher test loss than mutual learning. This implies that mutual learning has a regularization effect, which leads to better generalization. In independent training, it has been shown that using instance-bound sampling produces better representations than using class-bound sampling. We discovered that it also holds for the collaborative learning framework. We can observe that the sampling strategy which only uses instance-bound sampling achieves higher overall feature accuracy than those use class-bound sampling. Our research shows that mutual learning can help us learn more generalizable features than independent learning. Mutual learning framework is simple and easily adaptable to other cutting-edge approaches. Thank you for tuning in.